Hi, welcome to Lesson 12I, Parallelism. The goal of today's lesson is to learn how to apply vector operations to parallel vectors and use unit vectors effectively. So there are, of course, lots and lots of types of vectors in the world, lots of vectors that we've seen. Some of these vectors that we've looked at in the past have actually been parallel vectors. Some of them are of equal length, some of them are not of equal length, some of them point in the same direction, others point in opposite directions. So we can see that there are vectors of different types, of course. Whoops, that's not really straight. So we can just demonstrate a few different types of parallel vectors. So one thing that we need to discuss is about parallel vectors, and basically that two non-zero vectors are parallel if and only if they are scalar multiples of each other. So that means that if vector A and vector B are parallel, then there exists some sort of k. So vector A and vector B are parallel if and only if there is some scalar k that equates them. So then, therefore, we can see that they are parallel. If we have, say, vector A is, let's keep it simple, 1, 2, 3, and we know that vector B is -2, -4, -6, then we know that vector A equals k vector B. Therefore, in order for them to be equal, k is actually equal to -1/2. So if you were to multiply all of the components of vector B by -1/2, you would then get all the components of vector A. Okay, and that just shows then that the two vectors are parallel. Recall from earlier conversations about vectors. Vectors have magnitude and direction. So this is the magnitude of the vector. And this thing here, that's actually the unit vector. That's what gives it its direction. This little symbol on top of unit vectors is called a caret. Some people call hat, I say caret. So that indicates a unit vector as opposed to just the arrowhead indicating vector notation. Okay. So we also know that unit vectors have a magnitude of 1. Because they're called unit vector, it's 1 unit of magnitude, and because it's 1 unit of magnitude, that means that it won't affect the magnitude of the actual vector. It only is indicating the direction. So the the unit vector is like the steering wheel, and the magnitude would be, say, the accelerator or the engine or whatever that's driving the vector. So the magnitude gives basically the length of the vector, obviously, and the unit vector gives the direction, not affecting the magnitude at all. So the magnitude is a scalar. What we can do is we can multiply both sides of this equation by the reciprocal of the magnitude, like this. And so therefore, the magnitude of the vector v multiplied by the reciprocal of the magnitude of vector v, that just ends up being equal to 1. So on the right side, we're left here with just the unit vector, and we're left here with 1 over the magnitude of vector v multiplied by vector v, sometimes seen as vector v over the magnitude of vector v. So if we know that the unit vector is 1 unit, the magnitude of the unit vector is 1 unit, then if we take the magnitude of both sides, then we know that this side equals 1, and we've got this thing again, so the vector over the magnitude of all that, and then as we dismantle this a little bit, we've got 1 over the magnitude of v multiplied by the magnitude of v equals 1, and therefore we actually end up having, as I write this over here, the magnitude of vector v over the magnitude of vector v, which is essentially what we had over here, but I had to like simplify it or bring it down into its component parts first to show that that does indeed equal 1. So if we have some unit vector, we know it's going to be magnitude of 1. Any other vector parallel to that vector, so suppose vector A again, vector A would be some scalar multiple of that vector. So this is the unit vector. That's a representation of the unit vector. Unit vector multiplied by some scalar k will give us the other vector. Okay, and the unit vector is parallel to this. That k is just determining the magnitude of vector A by multiplying by this unit vector, which is unit 1, or 1 unit in length. So just recall that this thing is the unit vector. And two vectors, just because they're not pointing in the same direction doesn't mean that they're not parallel. So we can even say that vector A is plus or minus, or two possibilities of a vector that's parallel to the unit vector. There's plus or minus k times that unit vector. So if you're asked to find two unit vectors parallel to some certain vector, then you just do the plus minus, positive in the same direction, and the negative will flip the fraction, or flip the vector around into the opposite direction. And since we had so much fun with looking at the video on parallel vectors, or parallelism, let's jump right to section 12J, the scalar product of two vectors. And the goal of this part of the lesson is to learn how to multiply two vectors together and find the angle between two vectors. Up until now, we've been adding vectors and subtracting vectors and multiplying a vector by a scalar, but we have never actually multiplied two vectors together. Well, that's where the scalar product comes in. And the scalar product is also called the dot product. If we're given vector u being u1, u2, and u3, and vector v being v1, v2, and v3, then it is known, and there's a bit of a development of this which I won't get into, but it's pretty snazzy, if I can use that word, snazzy. U dot v, or the scalar product of vector u and vector v, ends up just being u1 v1 plus u2 v2 plus u3 v3. So just like when we were adding and subtracting vectors, we would add or subtract the like components. When we do the dot product, or the scalar product of two vectors, we multiply like components and then add them together.